Hello and welcome back to Fourier Transform, the video series where we talk a lot about this particular integral transform and what we can do with it. And in today's part 25, we will just look at an explicit example for the Fourier transform. However, as always, before we really start, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as a reward for your support, you can find a lot of additional material with the link in the description. And then without further ado, let's quickly recall the definition of the continuous Fourier transform as we have defined it in the last video. The case we've considered is that we have a Lebesgue integrable function f defined on Rn. And this one has a Fourier transform denoted by f hat. And it's defined by an integral which also gets a factor 1 over the square root of 2 pi to the power n in front. Moreover, the integral itself goes over the whole space Rn, and inside we find the product of this exponential function with f. And please note, in the exponent of the exponential function, the vector p and the vector x are combined with the standard inner product in Rn. So this guarantees that we always have a real number here behind the factor minus I. And with that we have it. This is the whole definition of the Fourier transform for functions defined on Rn. And please recall, we already know that this resulting function f hat is always a continuous and bounded function. So in this sense, it can be much nicer than the input function f. To see that, we will look at an explicit example as promised. And obviously it might be helpful to start with a quite simple example for our function f. Which means we start with the one-dimensional case and I first show you the graph of the function we consider. I want to have it equal to 0 except for an interval around the origin. So let's simply say this is the interval from minus delta to plus delta. And there the function should just be equal to 1. This means for the explicit definition of f, we just have to distinguish two cases. It's equal to 1 if x lies in the closed interval from minus delta to plus delta, and equal to 0 if it lies outside this interval. So in other words, we have a simple function which is obviously not continuous. And now we can use the definition from above to calculate the Fourier transform of f. In fact, this is quite simple because our dimension n is just given by 1. Which also means that the standard inner product here is just the product of two real numbers. And moreover, the essential part of the integral just goes from minus delta to plus delta. So there you see, this makes the whole calculation really easy. So we just have to integrate this exponential function, which means we have to use an antiderivative. Therefore, we have to divide by the factor in the exponent, which is given by minus I times p. And there you already recognize this only works if p is not equal to 0. Hence we should put this to the left hand side as an assumption from the beginning. And please note, we can do that without loss of generality because we already know that the resulting function here is a continuous one. So excluding one point does not lose any information at all. And now back to the antiderivative, there we just have to put in the upper limit and the lower limit. So you see, it's just a standard calculation for a one-dimensional integral. And as you know, what we get here is just the difference of two exponential functions again. And there you might already recognize that this can be written as a sine function. So please recall, sine of y is just given as 1 over 2i times e to the power iy minus e to the power I minus y. So this is what we can use here, and then we have a sine function where we put in p times delta. So the minus I in the denominator vanishes and we have a factor 2. And there we have it, this is our result, this is the Fourier transform of our given function f. And obviously we can make it a little bit nicer, and first we should bring the constants to the front. And then we can put the sine function together with 1 over p. And to make it clearer what happens here, we should write p times delta into the denominator. Which also means we have to multiply with delta on the right hand side again. Please note, writing it like that is helpful because what we find here is the so-called sinc function. And this one is a continuous function which has the value 1 at the origin. Hence, the essential result is that our characteristic function here has the Fourier transform given as the sinc function scaled with delta. Which means if delta grows larger and larger, the value at the origin for the Fourier transform also grows with delta. However, there you might also know that the sinc function is not a Lebesgue integrable function at all. In fact, if you integrate the absolute value of this function from 1 to infinity, and let's say we have sine of y divided by y, then we don't get out a finite number. This is quite interesting because we immediately get an example where the output of the Fourier transform is not an L1 function anymore. And now I would say, let's illustrate the whole thing by plotting the graphs. So here I have the original function f, where delta is chosen to be equal to 1. And now to the right I can also plot the Fourier transform, which is given as the sinc function. And please note, this one definitely goes into the negative values, and it has the maximum here roughly at 1, because we still have this factor in front. Therefore, I would say in the next step, let's jump to the case that delta is equal to 2. And there you see, our interval on the left gets larger, and also our peak here on the right. And now I would say, let's just increase it more and more to see what happens. So here for delta is equal to 6, you already see a lot of fluctuations and this high peak in the middle. Therefore, in the limit delta to infinity, the left hand side would just be the constant 1 function, but the right hand side would explode at the origin. In fact, this Fourier transform here on the right hand side approximates the Dirac delta function. However, this already goes beyond what we actually do here, because we can only use integrable functions on the left hand side. So we can make this delta as large as we want, but we cannot send it to infinity. However, in order to understand how the Fourier transform works, this limit process is still helpful. However, this is definitely something for another video, so I really hope I meet you again when we go deeper into the theory of the continuous Fourier transform. So I really hope I meet you again and have a nice day. Bye bye.